Okay, several things that you need to prove, just for practice in writing out proofs. Very easy to prove if you simply write them out using the conventions we have, letting u equal u1 dot 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 un, v equal v1 dot 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 vn, and you just write out what you've got and it works out. If you can do a little bit of algebra, and it's really pretty simple algebra. Okay, so prove that u dot v equals v dot u. I think we already kind of did that, but do it fresh. U dot v plus w, quantity v plus w is u dot v plus u dot w. It's a distributive law. V dot v is greater than or equal to 0, and they're equal if and only if v is the 0 vector. Now we proved something very similar, but again, if you just write this out and go step by step and simplify things, it works right out. And that's the case for most of these, okay? These are a little more complicated, but not bad. You should at least be able to write out what this side means and what this side means, and then do a little simplification. Same here, same here. If necessary, you can, and it's really not a bad idea, to just prove all these things in R2 and then see geometrically why they're true, because the geometry is really no different in higher dimensions. But ultimately, you want to prove it in Rn, starting from the definitions, not starting from some hand-waving intuition. You want to have that hand-waving intuition. There's nothing wrong with it. You just have to make it specific enough that you have confidence in it, full confidence. Okay? Okay, well, now we go on to the fact that u dot v is magnitude of u times magnitude of v times the cosine of theta, where theta is the angle between u and v. Now, no matter what dimension you're in, u and v are going to be in a plane. It's a plain old two-dimensional plane, and so is the vector v minus u, so you have a triangle in a plane. So you can apply the law of cosines. Now, there's a little bit to this. This is more difficult than the other proofs. It would be great if you would know how to prove this, because it might be something that you ask to prove for extra credit. Okay, but there's your picture. You got your u, you got your v, and you got your v minus u vector. You write these things out in symbols, do a little algebraic manipulation, apply a little bit of trigonometry, and it works out. Not trivial though. Some of these are pretty trivial proofs. These take a little bit more, because you've got to use a little more algebra. And this takes a little more than that, but it's still within the range of what some people might be able to do. Okay. Anyhow, you have this, so, what's the angle? Angle between, let's say, the vector 2, 3, -5, 1, call that v, and u, and I'm not writing those very well, equal to -1, 3, 7, 4. Now, this is in four-dimensional space. You can't even visualize it. But we can calculate it very, very easily. Okay, so calculate it. Calculate the angle. Okay, stop, do that, at least do everything you can. Okay, well, okay. Now, you might or might not have been able to calculate the angle, but certainly you can calculate u dot v. You can calculate magnitude of u, you can calculate magnitude of v, and you can write this down with numbers here, here, and here. U dot v is what? 2 times -1 is -2. 3 times 3 is 9, so that gives you 7. -5 times 7 is -35, so now you got -28, and you add 4, and you got -24. So I think this says, well, I'll write it out. U dot v equals -24. Put a question mark here. You can check my arithmetic, because I haven't done this previously. This is simple arithmetic. And actually, I'm probably going to get it right today. Some days you could forget it. Okay. Still, I might have already made a mistake, so check me. Okay, now, magnitude of v, well, 2 squared is 4, 3 squared is 9, so that's 13. 5 squared is 25, that's 38, 39. So that the magnitude of V is the square root of 39, and the magnitude of U is what? Well, okay, 1 squared and 3 squared is 10, and 7 squared is 59, and 4 squared, I've got to be careful here, is 65. Of course, talking while I say it, I'm not going to check it, give you the chance to catch me. Okay, so there we have it. So now we can write down this, not in general the way I would approach it, but if you haven't already calculated these and substituted them, that's what you need to do. Okay, so if you haven't done it, do it. In any case, we get negative 24 equals square root of 64 times the square root of 39 times the cosine of theta. Can you find theta? Well, I hope you can solve this for theta, but just in case you can't, well, I'm not going to say, solve this for theta. Okay, well, hopefully you've done that, but just in case, first of all, what's cosine theta equal? Okay, well, write it down if you haven't already. It's going to be negative 24 over square root of 64, square root of 39. So what's theta? Well, hopefully your trigonometry is not so decrepit with disuse that you know what to do here, but if not, it's the inverse cosine of the same thing that I just wrote down here. And then you can figure that out. Now, just to give you something to beat me on, I'll estimate it. That's about 8, that's about 6, so this is pretty close to 48, a little more than 48. So 24 over 48 would be 1/2. The inverse cosine of 1/2 is 60 degrees, or a little over pi radians. But the denominator is a little bigger than that, so I'm going to say that that's approximately, not pi radian, 1 radian, it's approximately 1. And that means 1 radian. Okay, if I write down an angle without any unit on it, it's a radian. Or that would be about 57 degrees, and I don't want to try to estimate it any closer than that. It'd be within a couple of degrees of 60 degrees. And it's actually going to be, okay, it's the inverse cosine of a negative, so it would have to be pi minus 1, not 57, 180 degrees minus that, about 123 degrees. Okay, so you can figure it out, see if my estimate is any good at all. And of course, the circular model of the cosine tells you that if the cosine is negative, around negative 1/2, then the angle has to be like this. And if you don't understand the circular model well enough to make that picture and at least validate this general idea, you really need to be, okay? So review this circular model. It's very important from where you are and where you're going. Okay, so you see that we can always calculate the angle between two vectors in any Euclidean space, any Rn space. Okay. And it doesn't have to be vectors that you can visualize. It works in 3-dimensional space, works in 2-dimensional space, works in 47-dimensional space.